Why should I need three-dimensional analysis for the plane capacitor? There is the analytical equation to calculate the capacitance in this case. I will create the new problem, specify the location of the problem files and the problem name. The problem type is electrostatics and the model class is plane parallel. For the plane parallel model class, I should specify the model depth. Effectively, I should specify this dimension. (0.1 meter). Here there is the geometry model editor window, and I should build the geometry model here. This is one of the plates, this is the second plate. Now here is the geometry model. Then I should assign some labels to geometric objects. For example, this is the dielectric. This is the plate with positive charge. And this is the plate with the negative charge. Once I have finished with the labeling objects, I may assign the physical properties to each label. The labels are listed here in the tree. For the dielectric, I specify the electric permittivity of the material. In my case, it's 4. For the negative charged plate, I specify electric potential. For my case, it's -5 volts. And for the positive plate, I specify +5 volts. Now everything is almost ready. I should build the finite element mesh, save all problem files, and run the simulation. And here you can see the field distribution inside the plate capacitor. I will adjust the field picture and switch on the vectors and the color map. Now you can see how the electric potential is distributed inside the capacitor and how the electric field strengths vectors are distributed. But my task is not only to simulate the field distribution inside the capacitor, but also to calculate the capacitance. There is a simple equation to calculate the capacitance. You should divide the charge by the potential difference. So I will build the integration contour. I will close the contour around one of the plates and calculate the electric charge stored on this plate. Now, if I divide the electric charge by the potential difference, I will get the capacitance. And you may check these values against the analytical solution. In analytical solution, I should multiply the electric permittivity of the dielectric multiplied by the electric permittivity of the free space multiplied by the plate area. 100 by 100 millimeters will be 0.01 square meters, and divide by the distance. In fact, the distance in my case not 5 millimeters but 10 millimeters, so it's 0.01. So this is 45.4 10 to the power of minus 12, because the permittivity of vacuum is 885 10 to the power of minus 12. So we can say I get the same value with QuickField. But plain capacitor is not that plain. There is the fringe field at the edge of the capacitor. And if I'm interested in simulation of the fringe field, I should add the air outside the capacitor. So I will let the field distribute outside the capacitor. This block will be the air. And the electric permittivity of the air is 1. Now I will build the mesh again and run this simulation. You can see the field is built outside the capacitor. And if I again measure the charge, you may note that the value is different from the one I measured when there were no fringing fields. But that was the two-dimensional simulation, and I take into account fringe effects on the top and on the bottom side of the plates, but there are similar effects on the front and on the back side of the plates, and I cannot take into account these effects in two-dimensional simulation. So eventually I have to run the three-dimensional analysis. I will change the problem type to the three-dimensional extrusion. And once I have done this, I can switch between two-dimensional and three-dimensional view. Now this is the three-dimensional model. But if I run the simulation now, again, I will take into account the fringe effects only on this side. To take effects here on the upper and in the bottom, I need to add the air block at here and here. So again, I switch to the two-dimensional model and add heights to objects. Here it is. Now I should assign label to each object. This is the air. And below the capacitor is the air too. This is the air block. This is the dielectric block, this one inside. And outside is the air block. I have the negative plate on that side. I have the positive plate and the air outside the capacitor, so I can take into account all the fringing fields. The next step is to build the finite element mesh. Here you can see the finite element mesh. I can use cut by plane tool to show you the mesh inside. And this is how it looks inside. Now I can save problem files and run the simulation. Again, I will use the cut by plane. You can see the fringe fields here. And if I change the cut plane position, you will also see the fringe fields here. So now I will take into account all the fringe effects in the plane capacitor. And again, my task is to calculate the capacitance. I will use the simple approach. I will select all the bodies and calculate the stored electric field energy. And we know that the capacitance value is the twice this divided by the potential difference square. So you can see 3.8. It was 3.5 in the ideal capacitor, but in real capacitor, the capacitance differ from the analytical value. And with QuickField three-dimensional analysis, we can calculate the real capacitor capacitance. Now that was the extrusion introduced in QuickField 6.0. But let's imagine that we have some defect, some inclusion inside the capacitor, some spherical of small radius. How should we simulate this? Well, let's switch back to QuickField. Now this is our geometry model, and here I should draw the defect, some cylindrical body. Yes, that's simple. Now I switch back to the three-dimensional. I will switch on the transparency. Here you can see the cylinder. In fact, I have the small bodies, small inclusion, so I should assign more heights to the cylinder. Again, I switch back to two-dimensional and specify the heights for my inclusion. from 0.5 to 0.6. Switch to three-dimensional. Switch on the transparency mode. Here it is. This is my inclusion. But you can see that the shape of this inclusion is not spherical. It's cylinder. I may adjust the height of this cylinder. But nevertheless, it is small, but it's a cylinder. With extrusion, I cannot generate this spherical shape. I cannot generate the cone or toroidal shape. QuickField 6.1, it is possible to import the geometry model from the majority of the computer-aided design programs. In QuickField, this type of geometry model is not compatible with extrusion, so I have to create a new problem, or I should change the problem type. So this is not three-dimensional extrusion, this is the three-dimensional import. And the model type is not more the MOD, but the M3D. So this is the three-dimensional model which supports importing the geometry. I'll press the import button and locate the file. This is the file that contains the three-dimensional model in step format. Here is the imported model. And if I look inside, again, I will switch on the transparency. You can see there is indeed this spherical object inside my capacitor. Now again, I should assign this labels to the objects. This is the dielectric. This is the negative plate. This is the positive plate. And if I hide the dielectric, there is the sphere. The air has permittivity of 1, while the dielectric has the permittivity of 4. Now let's show all the objects. I have the air sphere inside. I have the dielectric and positive and negative plates. Now again, I should build the mesh. And here you can see the finite element mesh. Again, I will use the cut plane to show you how the mesh looks like inside the capacitor. And we can save all problem files and run the simulation. And this is the result. We have the electric capacitor with the spherical part, place it inside. This is the spherical part inside. To highlight it better, I will switch to the electric field stress color plot.